Critics pointed out that there has never been a suggestion in the toxicology literature that mercury exposure would affect IQ, and that the 8-year period of these studies would be insufficient to reveal long-term effects of mercury exposure that may take decades to develop. But the first tangible sign that the argument in support of amalgam safety is faulty was the graph from the original DeRuren paper. It shows a decline in urinary mercury excretion in the amalgam group over the 8-year period. Since amalgam fillings continue to emit mercury and the children continue to get new fillings as time went on, why would they, especially the boys, excrete less mercury in later years? This effect is never explained by the authors, but it clearly reflects one of the best known toxic effects of mercury on the kidneys, inhibition of proximal tubuliform function. This means that mercury exposure poisons the body's ability to excrete mercury. To their credit, the CAT investigators collected exceedingly detailed records for each of their subjects. The data contained information on exactly which teeth had what kind and what size filling in which year for each specific child. A group led by David A. Geyer, sponsored in part by the IAOMT, was able to take those data and calculate an actual dose exposure to either amalgam or composite for each individual child. There are much more specific dose effects measurements revealed a different story than the original publications, which just lumped all the kids in the amalgam group or the composite group together. In this paper, data on urinary porphyrins, a biomarker of mercury toxicity, were part of the original collection of physiological data. Porphyrin markers were compared to actual exposure to amalgam fillings and were found to be correlated to amalgam exposure in a dose-dependent fashion. The actual dosed exposure data for the kids in Portugal's study also showed that their urinary mercury did in fact rise with exposure to amalgam. This was in contrast to the conclusions of the original study. A third paper by the Geyer group showed that, as might have been suspected, the effects of increased amalgam mercury exposure took a toll on the children's kidneys. There was a dose-dependent increase in urinary levels of GST, a biomarker of kidney stress. CPOX4 is a relatively common variant of a gene which codes for an enzyme in a porphyrin synthesis pathway. In this paper by one of the original CAT authors, boys with that variant gene are shown to be more susceptible to the effects of amalgam mercury exposure on their nervous system. Several other genes are known to increase a person's susceptibility to mercury toxicity. Another common one is alloprotein E4 gene, which has long been associated with an increased risk of early onset Alzheimer's disease and has a clear connection to the neurotoxic effects of mercury. Finally, another paper by some of the original authors of the CAT study showed that another common gene variant plays a role in the neurological effects of mercury exposure on children. In this case, it is a gene for metalmethionine, an important protein that affects how cells protect themselves from toxic metals. The study states that there is an increased susceptibility to the adverse neurobehavioral effects of mercury among children with relatively common genetic variants of metalmethionine. It's another demonstration of how some individuals are more susceptible to the toxicity of mercury than others. In the end, the CAT studies only proved what we already knew about dental amalgam, that they provide significant exposure to mercury and cause significant measurable physiological harm. We should notice, too, that all the follow-up papers that refute the original conclusions of the CAT studies were published in toxicology journals and not dental journals. There's been no mention at all about these follow-up papers in the dental press.